Dawn stretches a violet bruise across the Pacific while a container ship the length of 4 football fields glides westward, its steel boxes glowing in the first slant of sun. From the bridge the motion feels serene, yet 2 decks below the hull quivers with the pulse of a diesel engine 5 stories tall, firing 6 strokes a second. Laptop-sized computers trim every fuel injection, pumps hum coolant through a labyrinth of pipes, and surplus exhaust heat spins a steam turbine that lights the galley and the gym. Most people never see this hidden choreography, but without it 90% of everything we eat, wear, or tap on a screen would never reach our shores. The profession that makes it all work is marine engineering, a craft that merges heavy machinery, sophisticated software, and environmental science to keep the global fleet alive. Marine engineering is often summarized as systems and power for anything that floats, yet that tagline barely hints at its scope. A modern cruise ship resembles a floating city more than a vehicle. It generates more electricity than a wind farm, produces its own fresh water, incinerates rubbish, stabilizes itself in force 9 seas, and must entertain thousands of passengers while obeying half a dozen regulatory codes. Every one of those functions, propulsion, electricity, plumbing, climate, waste, data, is designed, integrated, and continually nursed by marine engineers. They are equal parts mechanical designer, electrical integrator, fuel chemist, corrosion specialist, and emergency troubleshooter. They think in decades because the ships they steward may trade for 30 years, yet they must react in seconds when a filter clogs or a bearing overheats 300 miles from land. To grasp today's challenges, it helps to revisit the field's evolution. When Robert Fulton's Clermont began steaming up the Hudson in 1807, critics predicted her paddle wheels would terrify the fish, but within a generation scheduled transatlantic mail packets were advertising arrival dates more reliable than any sailing ship could claim. Early marine engineers were heroic boilermakers, coaxing fragile wrought iron shells to hold steam without bursting. Metallurgy advanced, pressures rose, compound expansion engines let ships travel twice as far on the same coal. In 1858 Isambard Kingdom Brunel launched Great Eastern, an iron leviathan with a double bottom, watertight bulkheads, and a hybrid of paddle wheels, screw propeller, and auxiliary sail. She set no commercial records, yet she proved that integrated systems thinking could scale vessels beyond the dreams of sail-era designers. The next revolution roared out of a German workshop. Rudolf Diesel's compression ignition engine, exhibited in 1900, soon leapt to sea. In 1912 the Selandia steamed from Copenhagen to Bangkok on twin diesel engines, burning half the fuel of comparable steamships and needing a fraction of the crew. By mid-century slow-speed diesels ruled merchant shipping, their 2-stroke pistons longer than a London taxi and so thermally efficient that even today no other prime mover matches their specific fuel consumption. Gas turbines arrived for warships, offering staggering power-to-weight ratios, and in 1955 the submarine Nautilus showcased nuclear propulsion, effectively unlimited endurance beneath the ice. Commercial operators balked at reactors' costs and politics, yet the experiment underlined how tightly marine engineering intertwines with geopolitics. The 1960s brought containerization. Ships ballooned from 3,000-ton coasters into 15,000 TEU giants whose engines stand taller than cathedral domes. A single rotation of such a vessel can move more freight than a small nation imports in a year, but only if its machinery remains flawless. Near the turn of the millennium new anxieties surfaced: global warming, sulfur pollution, invasive species. The International Maritime Organization's 0.5% sulfur cap in 2020 forced a reckoning with scrubbers, low sulfur blends, and liquefied natural gas. Engineers accustomed to the reliable chemistry of heavy fuel suddenly had to model cryogenic tanks, exhaust catalysts, and particulate traps that would be laughed at on a 1960s blueprint. Stand now on the engine room gratings of a modern container ship and the scale becomes visceral. The main engine delivers 80,000 kilowatts at 80 revolutions per minute, each piston stroke bigger than a London underground tunnel. Scavenged air is compressed, cooled, filtered for dust, and fed into cylinders where precisely metered heavy fuel ignites. Jacket water loops carry waste heat to a steam generator that powers pumps and hotel loads. Lubricating oil circulates through centrifuges that spin out soap. Overhead a forest of sensors reports every temperature, pressure, and vibration to a control room bristling with screens. A duty engineer patrols at dawn, feeling casing temperatures with the back of his hand, sniffing for oil mist that could presage a crankcase explosion, logging every parameter so anomalies can be compared with shoreside analytics. A continent away in a design office, another marine engineer manipulates a digital twin of that same vessel. Computational fluid dynamics software simulates how micro-bubble lubrication might reduce hull drag by 1%. Propeller blade outlines are nudged in sub-millimeter increments to avoid cavitation. A piping specialist reroutes ballast lines so they cross fewer fire zones, shaving weight and insurance premiums. Environmental engineers tweak catalytic reduction reactors to meet nitrogen oxide limits without burning costly urea. The diversity of tasks, metallurgy, software, thermodynamics, finance, makes marine engineering less a single job than an ecosystem of overlapping specialties. Propulsion remains the headline act. Two-stroke diesels dominate deep-sea trade because their long strokes and low speed squeeze unmatched thermal efficiency from cheap residual fuel. Medium-speed engines paired with generators power cruise ships and dynamic positioning vessels where flexibility matters more than raw efficiency. Gas turbines slot into frigates and fast ferries that prize sprint speed. Dual-fuel engines can burn LNG to slash particulate and sulfur emissions but must still switch to oil if a gas bunker is unavailable. Pure battery propulsion, once dismissed as fantasy, now drives dozens of Norwegian ferries that recharge megawatt-hours in 10 minutes thanks to shoreside supercapacitors. Hydrodynamics binds machinery to the hull. A bulbous bow can slice wave resistance if the ship almost always sails full, but on a tramp route that loads light one week and heavy the next it may waste fuel. Propeller end plates, rudder bulbs, and pre-swirl stators reclaim energy otherwise lost in rotational slip. Engineers model Reynolds numbers in the millions, tweak blade pitch, and sometimes accept a tenth of a knot less speed to save 10 tons of fuel a day. Every tweak compounds over a fleet. A 1% gain multiplied by 50,000 ocean-going ships equates to millions of tons of CO2 avoided annually. Materials science is a perpetual war against corrosion and fatigue. Saltwater, chloride ions, and stray electrical currents conspire to pit even stainless steels. Cathodic protection systems pass an intentional current through sacrificial zinc anodes. Smart coatings embed graphene flakes to slow oxygen diffusion. Finite element models predict stress concentrations in crank webs. Scheduled borescope inspections verify reality before cracks propagate. A fracture in an 800mm hull is not merely a repair bill, it can immobilize a billion-dollar cargo, block the Suez Canal, and ripple through supply chains worldwide. 20 years ago, electrical engineering played a supporting role. Today it is the ship's nervous system. High-voltage ring bus switchboards distribute 11 kilovolts to thrusters, reefer points, and bow cranes. Power management software can black start a dead ship, shedding non-essential loads in milliseconds to save the propulsion plant. Bridge integration networks link gyro compasses, radars, satellite domes, and autopilots into a single Ethernet backbone. Every node is a potential cyber target. Marine engineers now collaborate with security specialists to air-gap critical automation so ransomware can't set an engine to full astern. Environmental regulations require their own hardware. Ballast water reactors sterilize invasive organisms with ultraviolet light or ozonation. Sewage plants employ membrane bioreactors that meet discharge rules tougher than those on land. Exhaust scrubbers spray alkaline water to bind sulfur oxides. Selective catalytic reduction units inject urea to convert nitrogen oxides into benign nitrogen and water. Shore power inlets let ships draw renewable electricity in port, switching off diesel generators so dockside air stays breathable. Every advance introduces new headaches. The hardest dilemma now is fuel choice. Owners ordering a ship today must decide whether to fit conventional engines, dual fuel gas capability, or gamble on ammonia and methanol designs still on the test bench. Each path demands unique tanks, safety zones, sensors, and crew competencies. Capital risk thus migrates to the engineer's office, where machinery spaces must be future-proofed so valves, pipes, and pumps can handle tomorrow's refrigerants and fuels without structural surgery. Data overload is another modern concern. Vessels stream gigabytes per hour to shoreside fleet centers promising predictive maintenance, yet crews can drown in graphs if dashboards lack context. Turning vibration harmonics into actionable job cards requires statistical fluency as well as mechanical intuition. Engineers are writing algorithms that flag only deviations with clear causal chains, freeing watchkeepers to focus on root causes rather than chasing phantom anomalies. Climate resilience shapes hull scantlings and machinery margins. Sea surface temperatures creep upward, forcing redesign of seawater pumps and condensers once sized for 25-degree tropics but now slurping 30-degree brine. Wave height distributions are shifting. Ship structures calibrated to a 20th century 100-year storm may face supercharged cyclones. Naval architects and marine engineers collaborate on probabilistic load cases, designing for wider envelopes rather than single-point extremes. Every challenge breeds innovation. Battery electric ferries like Norway's Ampere recharge 6 megawatt-hours in 10 minutes, eliminating diesel smoke in fjords. Rotor sails, spinning cylinders exploiting the Magnus effect, deliver up to 10% fuel savings when winds align, without altering schedules. Digital twins replicate entire ships in the cloud, updated every 5 seconds by onboard sensors. If a bearing trends hot, the twin reruns thermodynamic models, predicts failure within 40 hours, and orders spares to meet the ship in Rotterdam before downtime occurs. Autonomy looms larger each season. The Norwegian coastal freighter Yara Birkeland completed unmanned trials in 2022, monitored from a shoreside control center. Such projects shift engineering focus from manual watchkeeping to fail-safe redundancy. Pumps must restart after brownouts, valves must default to safe positions, and fire detection loops must trigger suppression without human intervention. Cybersecurity and machine decision ethics now live alongside shaft alignment and lube oil viscosity in the marine engineer's knowledge stack. The profession's entry paths mirror its diversity. Many engineers earn a 4-year university degree in marine, mechanical, or ocean engineering, taking electives in ship design, thermodynamics, and maritime law. Programs partner with shipyards and class societies for internships where students crawl ballast tanks, witness engine shop tests, and stand watch in simulators. Others follow a maritime academy route, spending alternating semesters at sea and in class. Cadets graduate with a STCW Officer of the Watch certificate and climb through ranks, 4th, 3rd, 2nd, and Chief Engineer, by accruing sea time and passing rigorous oral exams. Promotion is swift. A 27-year-old can be responsible for power plants equal to a city's. Seagoing life appeals to some for its camaraderie and adventure. A chief engineer may sail 14 weeks on, 14 off, earning 6-figure pay and witnessing sunsets few desk jobs offer. Shore-based roles are just as varied. Design consultancies craft hydrogen bunkering manifolds, class surveyors inspect welds and witness trials, engine makers dispatch field reps to troubleshoot turbo surges worldwide, offshore wind developers hire marine engineers to install turbines taller than skyscrapers. The maritime economy's global reach means a career might include months in Korean shipyards, winters in Norwegian fjords overseeing battery retrofits, and summers on Gulf of Mexico platforms fitting carbon capture units. Looking ahead, 3 megatrends will shape marine engineering. First is the decarbonization quest. Liquefied natural gas offers immediate reductions in sulfur and soot, but it is still a fossil fuel. Blueprints for ammonia-ready engines emerged in 2023, commercial deliveries may sail before the decade ends. Engineers must master materials that resist ammonia's corrosive bite, design double-walled pipes with nitrogen purges, and write control laws that prevent explosive mixtures in crankcases. Methanol, easier to handle but less energy dense, may power container ships on green feedstock. Fuel cells, solid oxide or proton exchange, could provide silent auxiliary power. Each option demands fresh thinking in tank placement, ventilation, crew training, and emergency response. Second is autonomy's march. The International Maritime Organization is drafting rules for maritime autonomous surface ships, while classification societies have already published guidance notes. Coastal feeder routes and harbor tugs are likely first adopters, monitored by shore-side engineers who may one day supervise entire fleets through augmented reality dashboards. The Marine Engineers Toolkit will then include LiDAR calibration, sensor fusion algorithms, and remote restart scripts alongside torque wrenches and feeler gauges. Third is climate adaptation. Arctic shipping lanes open longer each year, demanding hulls that combine polar-class ice reinforcement with open water efficiency. Tropical cyclones intensify, so dynamic weather routing software must adjust more aggressively, and engine room ventilation must cope with hotter intake air. Hull coatings will need to repel ever hardier fouling organisms as oceans warm. Marine engineers will design systems that can burn zero-carbon fuels, navigate unpredictable weather, and lock down against cyber and physical threats. The stakes are colossal. A single large container ship saves 1 ton of fuel for every 2% improvement in propulsive efficiency. Multiply that across the global fleet and the savings dwarf entire national emissions. A flawlessly maintained LNG plant prevents methane slips more potent than CO2. Engineers who choose hull steel wisely avoid catastrophic brittle fractures that could trigger ecological crises. In other words, decisions made in design offices and engine rooms ripple through climate graphs, grocery prices, and national security briefings. None of these responsibilities dampens the romance of the job. Stand on a forecastle at dusk, feel the hum of machinery through the deck, and sense 2 centuries of ingenuity beneath your boots. Marine engineering remains a calling for people who relish puzzles that mix combustion chemistry with software logic, who can swing a spanner 1 hour and model wave spectra the next, who thrive on the knowledge that their calculations keep billions of dollars of cargo moving. Whether managing a battery ferry in a Norwegian fjord, tuning a gas turbine on a frigate, or writing control software for an autonomous container feeder, marine engineers form the quiet network that keeps the planet's arteries open. If this exploration left you curious, consider joining that network. Visit maritime academies, tour engine rooms, tinker with CFD software, and read accident reports. They are the best textbooks ever printed. The next decade will need minds capable of welding old-school practicality to frontline innovation. Bring patience, curiosity, and a willingness to learn from salt and steel. The ocean may be vast, but for marine engineers it is an open laboratory where every wave, bearing, and kilowatt tells a story worth decoding. Like the video, subscribe for more engineering deep dives, and share which future technology, ammonia engines, rotor sails, or digital twins, excites you the most. Until next time, fair winds and following seas.